Lee, by the way, there's still a blue gray mark on your screen, right?
How about you?
Yeah, it's gone now.
Okay, good.
Okay. Welcome everybody to the last session of STOC. We have the complexity session 10B. We have a great set of 4 talks. We have, as is this one customary, each talk will be about 10 minutes each. The actual presentation will be 5 minutes, followed by 5 minutes of question answers. Response. And if you have any questions, please post your questions either on the Q&A or raise your hands. And depending on the amount of time we have, we'll answer as many questions as possible. And yeah, so let's get started. Our first speaker is Lee Chen, who will be speaking on strong average case circuit lower bounds from non-trivial de-randomization.
Hi, thanks for being here. So first, let me get started on the motivations of this work. So first, there's some oversimplified history and the motivation for circuit lower bounds and the de-randomization. So first, since 1980s, people wanted to prove NP is not equal to P via proving lower bounds for stronger and stronger circuit classes. And currently, one frontier question is to prove stronger average case circuit lower bounds for the ACC0 circuits. And I'll be defining that in a moment. Another big question complexity is about de-randomization and the PRGs. Since the 1980s, people wanted to show P equals BPP by constructing PRGs for stronger and stronger circuit classes. And one frontier question is actually getting PRGs for AC0 parity. And for that, we need stronger average case lower bound for AC0 parity. And I'll define them in a moment. And you can also check the workshop 6 on related question BPO equals L. So here, first there's some evolution of circuit lower bounds. First, people studied AC0 circuits, which are constant depth and or not circuits of unbounded finding. And that's beautiful line of work showing that parity is hard for AC06. The parity function and the mod P function is that the function outputs 1 if and only if P does not divide the number of 1s in the input. And the parity is just mod 2. The next step is to add parity into the number of available gates. Then people study AC02 circuits, which is AC0 circuits extended with parity gates. And then Boff and Smolensky showed mod 3 is hard for AC02. Then people just add mod 3 to the available gates. Then we arrive at AC06 circuits, which is AC0 extended with mod C gates. Having mod 3 is equivalent to having both mod 2 and mod 3. So AC06 and here's a diagram of how we arrive here. It seems it shouldn't be much stronger than AC0 parity, but unfortunately it has been open for 20 years whether NX contains a function that cannot be computed by a polynomial size AC06 circuit of even depth 3. And NX is a non-deterministic exponential time. The progress basically stopped here until in 2011, Williams proved that NX does not have polynomial size AC0 circuits. And the AC0 circuits is a union of AC0M circuits for all constant M. So it contains AC06 and AC02. Since then, there's some subsequent developments on this front. In 2017, people proved that NX cannot be half plus 1 over polynomially approximated by polynomial size AC0 circuits. So now it extends to average case. And then in 2018, people proved that non-deterministic to the polylog time does not have polynomial size AC0 circuits. So this makes NX much smaller. Last year, Chen proved that NQP cannot be half plus 1 over polylogarithmically approximated by polynomial size AC0 circuits. Our approximation is over uniform distribution. So this improves all above. So the next question here is, can it be improved to half plus 1 over polynomial? Another motivation is on de-randomization. People wanted to prove P equals BPP by building PRGs. And for this purpose, we need to have a PRG for P-such poly with a log n incidence. But unfortunately, we don't even have PRGs for AC02 with sub-polynomial incidence. The reason is that we don't have strong enough average case lower bounds against AC0 parity circuits, because using the Williamson paradigm, we need a half function that cannot be half plus 1 over n approximated by AC02 circuits. And currently, the best lower bound is for majority, which is only half plus 1 over root n, so which is not enough for building the PRG. So in this work, we prove that non-deterministic quasi-polynomial time cannot be half plus 1 over polynomially approximated by polynomial size AC0 circuits. And this improves the half plus 1 over polylog result in chain 19, and also surpassed the half plus 1 over root n barrier for AC0 parity before. And the techniques, I don't have time to cover them at all, but there's some keywords, and you can check the longer video. And there's some new development which you can look quickly, as I'm running out of time. And that's it. Thanks. Any questions?
Any questions? I don't see any questions, but if you feel free to raise your hand. And, so yeah, so I had a question from Mark. So I recall having read any abstract and stuff that one of the main tools that goes into is PCPs and stuff. So what aspect of the PC, and you have to actually modify the PCPs a fair amount to this one. So what aspect of PCPs do you need, and what's the modification you needed to do in order for your result?
Oh, so here so the PCP we did is something that given the hard distance and the witness, you need to have an NC1 circuit for computing the PCP proof.
This is the verifier, the running time of the verifier. You're asking the complexity of the verifier, or?
I'm asking the complexity of constructing the PCP proof given the witness for the original NP computation. So you are given the witness of the original NP computation, and you want to construct from that a PCP proof for the PCP verifier and then so we build an NC1 computation which can transform the NP witness to the PCP witness.
Okay. Any other questions? Yeah, Eric has a question.
Yes, you say that you curious if you do you need all the power of NC1 or is TC 0?
Oh, so yeah, actually the only thing you need is some like multiplication of polynomials. So I guess TC1 suffices. Yeah, sure.
Okay.
Thanks. It's a good question. Yeah.
Yeah, so there's one question from Marco.
Oh yes, so we can have a NE capital NE running time PRGs for ACC0 circuits, but the seed length is something like the inverse function of a half exponential function. So you can think about the seed length as something like 2 to the log n to the epsilon for any constant epsilon. Yes, it will be interesting to see if we can get a PRG for like just a deterministic PRG without the NE capital NE computation.
Let's have a sort of a virtual clap. Let's thank Li Ji for this talk and move on to the next.
Yeah, thanks so much. Oh, I probably shouldn't stop.
So Li Ji will be giving the next talk also.
Shall I start now?
Yeah, so the next talk is on sharp threshold results for computational complexity. by Li Ji Chen, Si Jin, and Ryan Williams, and Li Ji will be giving the talk. Yeah.
Thanks so much for coming again. So the motivating question for this talk is, how far are we from proving major lower bounds? And we all know can prove some weaker lower bounds, for example, against De Morgan formulas of size subcubic. But we don't know how to prove strong lower bounds, for example, NP not in NC1, which is equivalent to NP that not have De Morgan formulas of polynomial size. So can we quantify how far we are from various open questions like NP not in NC1? Heuristically, from the above, it seems we are closer to an n to the 3.01 formula lower bound than we are for NP not in NC1. This intuition could be wrong. There's a recent harness magnification papers shows that some weak lower bounds are actually as hard as to prove as strong lower bounds. This paper will show some extreme magnification theorems, which we call sharp threshold for complexity. So let's begin with the definition of the problem. So the minimum circuit size problem is a problem that you are given a function, you are given a truth table, and you want to ask that f has a circuit of size at most s. S is a function on the input length, m. So we know MCSP is clearly NP. And we believe MCSP with even very small m is not in p-size poly. And McKay, Murray, and Williams shows that if one can show MCSP does not have n times polylog n size circuits, then this will imply NP not in p-size poly. So a small lower bound, a weak lower bound for MCSP will imply some big breakthrough. There are many other results on this front. And I suggest you to check Eagle's talk in the workshop for more out of it. Let's see two examples of harness magnification theorems. The first one is for general circuits, and I just described. But for general circuits, the best lower bound we have is 5 times n for De Morgan circuits, and 3 plus 1 over 86 times n for 4 bases. And as you can see, we don't have good techniques for proving lower bound stronger than that, like n times polylog n. So it seems relatively we are far from the n times polylog n bound because itself will be a breakthrough. On the other hand, for De Morgan formulas, that's also a magnification theorem shows that if one can show MCSP does not have n to the 3 plus epsilon size formula, then P space is not in NC1. And the best known lower bound for MCSP is a subquadratic one. Therefore, one can see the gap between what we have and what we want is only n to the 1 plus epsilon. And in this paper, we show some new results with very sharp threshold. We can prove a lower bound of n to the c for some task L. And n to the c plus epsilon lower bound for any epsilon would imply a big breakthrough lower bound, like NP not in p-size poly or NP not in NC1. And we also get some magnification results for other tasks, also with sharp thresholds. So let's see. First, let me define what is a probabilistic formula. It's a distribution f over De Morgan formulas. And we say f computes a function f if for all x is correct with probability at least 2/3. And we show that if MCSP does not have n squared times polylog n size probabilistic formula, then P space is not in NC1. And also, we give a complementing lower bounds that MCSP does not have n to the 2 minus 1 over log n size probabilistic formulas. So the gap is only n to the epsilon. And we remark that there are cubic size lower bounds against probabilistic formulas for dense version of MCSP. And we also consider explicit proofs. And explicit obstruction against SN size formula is an algorithm that in deterministic polynomial time, it prints a polynomial size list, xi and fi, such that every SN size formula is inconsistent with the partially defined function f. So at least one input-output pair will refute this formula for computing f. We show that there is an explicit proof that parity requires formula of size n squared. But also, we also show that an explicit obstruction against n to the 2 plus epsilon size formula for any function will imply it has no subexponential size formulas. There are some open problems for this, and you can take a quick look over them as I'm running out of time. So thanks for coming. That's the talk.
Thanks, Lichi. Any questions? Salil, yeah. Salil too. Salil, go ahead.
Oh, yeah, great. So in terms of interpreting the results, one way to interpret is that crossing this threshold of like n cubed or n squared is hard. Another one is maybe that like MCSP is a hard problem to focus on, and maybe we should look at other problems. Which way does your intuition go on that?
Yeah, I actually think MCSP is probably the right function to work on, because studying more of the MCSP can give you the intuition, which probably leads you to the required lower bound, and all results state exactly that. If you can prove stronger lower bound for MCSP, then it will give you breakthrough lower bounds. I'm probably more optimistic. I mean, I'm a grad student.
Great, thanks.
The next question is from Marco in the Q&A. Marco has a question. Is there an interesting notion of explicit obstruction that gets the target circuit as input?
Yeah, so actually this is called a refilter. So a refilter takes both the formula or the claimed circuit and then try to come up with a counterexample. And usually it's called a refilter, and it's studied in many previous works, I think. And what we did can be seen as an oblivious refilter, which does not look at the given circuits or formula.
I had a question.
Go ahead.
So the notion of explicit obstructions, right? So here the sharpness is with respect to for which size circuits are you constructing this obstruction, right? So just like if I draw a parallel with like the notion of hitting set, is there something known for example, even for a parity, you have an explicit proof, but if you vary the size parameter, like the size of the list that you want to print, is there some result like that known? For example, if I have say n cube size list, but getting a n squared size list would imply a lower bound. Is there something like that known?
Yeah, I mean, as far as we are, I think all techniques do not care about the size of the list as long as it's small, like polynomial or even quasi-polynomial should be fine. I think even if we have a quasi-polynomial size list, it can give you some lower bound, but may not be as strong. So the size of the list is not very important here. The more important parameter is the size of the formulas.
Okay.
Time for one. Nicholas has a question. Nicholas, go ahead.
Hello, can you hear me?
Yeah, sure.
Okay,
Yes.
so it seems like some of these threshold results give very powerful bounds and come very.
Sorry, Nicholas,
Hi.
can you repeat? Yeah.
Okay, I just got reset.
Yeah.
So it looks like many of these sharp thresholds and hard mismagnifications theorems are coming very close to some problems that have resisted attack for many years. Do you think what this is showing is that there's going to be a wave of new progress on these problems, or is this more likely showing that actually some of these threshold points are much more significant than they might look at first glance, and therefore in some sense much harder to get?
Yeah, I think both views are valid. I mean, of course the threshold points are much more significant because crossing the threshold, we will have major breakthrough. But also, I'm optimistic that maybe combining with some other techniques, we can really cross the threshold and get the result we want. But I guess we need some more insights and combine them with the highest magnification.
Okay, thank you.
Okay. No questions. So thank Liji again, and I want to keep our next speaker, Srikanth. Can you share it? Liji.
Actually,
okay, my slides visible? Can you hear me, Prahlad?
Yes, yes.
So yeah, tell me when I can start.
Yeah, we can get started. Our next speaker is somebody back from home, a few kilometers from my place. I'm looking in at 3 in the morning. Srikanth Srinivasan from IIT Bombay. He'll be speaking on a robust version of Hegedus lemma with applications.
Thanks, Prahlad. Yeah, Prahlad said it's 3 a.m. here in India. That's just coffee keeping me going at this point. Yeah, feel free to ask me questions, wake me up, do something. Yeah. So I'm going to be talking about a robust version of Hegedus lemma, which is a nice lemma in combinatorics with some applications to theoretical computer science. So let me start off with the statement of Hegedus lemma. So this is a lemma about polynomial functions with a hypercube. Okay, so this is my picture of the n-dimensional hypercube. And let's take two different layers in the n-dimensional hypercube. So let's look at points of weight k for some integer k, and points of weight k plus q for some other integer q. Okay, and so Hegedus lemma at a high level asks about how well polynomials can distinguish between these two weights in the hypercube. Okay, so slightly more formally, the question is, what is the lowest degree polynomial that vanishes at all points of weight k, but does not vanish at any point of weight k plus q? Okay. So the answer to this question somewhat depends on the field f. So for this talk, let me just work with the field f2. Yeah. And so for example, so in this setting, suppose that we take k equals n by 2. Okay, so k is n by 2, and let's say q is 1. So we're trying to distinguish between these two weights. Now consider this very simple polynomial, just sum all the variables. So this polynomial vanishes at all points of weight n by 2. I'm assuming n by 2 is even here, and does not vanish at any point of weight n by 2 plus 1. So this distinguishes between these two weights. So now let's change the setting a little bit, and let's look at the case when q is 2. So suppose I want to distinguish between n by 2 and n by 2 plus 2. You can see that this polynomial no longer works, right? It still vanishes at all points of weight n by 2, but also vanishes at all points of weight n by 2 plus 2. Okay, so it does not distinguish between these two weights. And it's a cute exercise to show actually that there's no degree 1 polynomial that can do this. Okay, so there's no degree 1 polynomial that distinguishes between these two weights, but there's a simple degree 2 polynomial that does it. So this polynomial. It's the elementary symmetric polynomial of degree 2. And you can show that it vanishes at all points of weight n by 2 and does not vanish at any point of weight n by 2 plus 2. Okay, so more generally, suppose I want to distinguish between weight n by 2 and n by 2 plus 2 to the s. So q is a power of 2 here, and 2 is the characteristic. You can show that there's a polynomial of degree 2 to the s that distinguishes between these two weights. This is just a straightforward generalization of the example on the last slide. And the way to prove this is via either Lucas's theorem. So this is a theorem from elementary number theory, or via polynomial interpolation. Okay, so there is a polynomial degree 2 to the s that distinguishes between these two weights. And what Hegedus lemma says is that this is stacked. Okay, so there is no lower degree polynomial that can do this. Okay, so this lemma is actually a little bit more general than this. It works for various k and q, but this is in a nutshell what it says. All right, so what's the robust Hegedus lemma, which is the main lemma that we prove in this work? So now we sort of slightly weaken the constraints in the polynomial. Instead of asking that it distinguish exactly between these two layers, we ask that it approximately distinguish between these two layers. So that it vanish at most points of weight k, all but an epsilon fraction, and that it be non-zero at most points of weight k plus k. Okay. And again, let's work in the setting where the field is f2 and q is a power of 2. And so now note that we've got like a weaker constraint of the polynomial, right? And in fact, in this setting, you can actually come up with lower degree polynomials that do this approximate distinguishing. Okay, so in particular, if q is a large number, what you can do is you can simply sample a few random inputs and check if you get more ones than zeros. Okay, and this will give you a good idea of whether you are at weight k or weight k plus 2. So you can come up with, via sampling, you can actually come up with lower degree polynomials that distinguish between these two weights. But as you can imagine, as Q gets smaller and smaller, the sampling bound gets slightly worse. And the main result is that when the sampling bound does not work, when the sampling bound starts to get bad, then in fact you recover the lower bound of Q from the last slide. Okay, so the degree in general is at least the minimum of what you get from the sampling bound and the interpolation bound. Okay, and that's the main result of this paper. Okay, so to actually give you the formal statement of this result is a little bit tedious, but let me give you an interesting instantiation of the parameters. So suppose K is something like n by 2 minus root n, and K plus Q is something like n by 2 plus root n. Then in this setting, the lemma says that any such polynomial must have degree at least a constant times root n. Okay, so that's the statement of the lemma. So now there's an interesting lemma about polynomials, but it's reasonable to wonder why is this interesting for theoretical computer science, and where does this fit in among other things we know about polynomials that we find useful? Well, there's a nice comparison to a classical theorem in complexity theory due to Smolensky. So let me just compare this result with that one. So this is again the theorem that I stated, the lemma that I stated on the last slide. Okay, and there's this very nice theorem of Smolensky, which let me state in a similar language. So what Smolensky showed was that if you have a polynomial that vanishes at most points of Hamming weight less than or equal to n by 2. Okay, so that's in this part of the hypercube. And does not vanish at most points of Hamming weight greater than n by 2. That's this part of the hypercube. Then any such polynomial must have degree at least a constant times root n. Okay, so you can see that these two lemmas are very analogous to each other. But the slight advantage of this one in certain situations is that it assumes very less about the polynomial. Well, it assumes a little bit less about the polynomial than Smolensky's theorem. So Smolensky's hypothesis involves essentially the whole hypercube, whereas the hypothesis here essentially involves the behavior of the polynomial on just on these two level sets, which is comparatively a smaller fraction of the hypercube. Okay, so as a result, this lemma can actually be used to sharpen many consequences of Smolensky's theorem in complexity theory. So in particular, we use this lemma to give optimal degree lower bounds for something called the coin problem. We use this lemma to give optimal probabilistic degree lower bounds for all symmetric functions over fields of positive characteristic. We also use this lemma to prove a robust version of Galvin's problem, which is actually a problem in extremal set theory. And we use this lemma to give a robust version of that. Okay, so I'm more or less out of time, so let me stop here. Thanks. So Prahlad, you're muted. I can't hear you.
Yeah. Any questions? Yeah. So Adrian has a question on the Q&A. Question is, what is known about the degree of a distinguishing polynomial when the field is reals?
So when the field is reals, actually the question is not very interesting, because you can, so suppose I want to distinguish between weights k and k plus q, I can just look at the polynomial, sum all the variables and subtract off k. So this is always going to be 0 at all points of weight k and be non-zero at all points of weight k plus q. So there's a polynomial degree 1. So the question is not really very interesting. It's really interesting over fields of positive characteristics.
Russell has another question. So can you show that any functions of smaller degree is unable to solve coin problems?
Right. So yeah, exactly. So what we do using this lemma is that we give an optimal degree lower bound for polynomials solving the coin problem up to all errors. So the coin problem, for roughly those who don't know, is the problem of distinguishing between two coins, one that is heads with probability half plus delta, some parameter delta, and the other which is, let's say, heads with probability half minus delta. And using this lemma, what we're able to show is that any polynomial that solves the coin problem with error epsilon has degree 1 by delta times log 1 by epsilon. So it's some function of delta and epsilon, and it turns out to be the right function for all delta and epsilon. So yeah, so as a result of this, we can get tight lower bounds of the coin problem.
Aditya has a question. Are k and k plus q necessarily near n by 2?
So that's a great question. So yeah, so there is some, I put them there for a reason. The result is simplest to state in that setting, but essentially morally the result is always true. So either you can sample or you have to interpolate. So when k goes far away from n by 2, sort of sampling becomes a little bit easier. And you can see this when you sort of run the Chernoff bound or the right version of the Chernoff bound. So when k goes far away from n by 2, you get some sort of messy dependence on k, but it's essentially whatever comes from Chernoff.
In other questions? Okay. Actually, I had this regarding these robust versions. For say the robust version of Galvin's theorem, is it just a plug and play? That is, use the robust version of the Hegedus lemma in the original proof and you get the robust version, or do you have to do some more tailoring?
It's the high level details are exactly the same. It's hardly any change, but there are some messy technical details that one needs to handle. It's not exactly plug and play, but all the interesting stuff is already in Hegedus's original proof that solved Galvin's problem.
Okay. Any other questions? Let's thank Srikanth. And let's move on to our next speaker, Ashwin.
Okay, let me just share the screen. Okay, so can you see the screen?
Yes.
Okay, very well. So in this work, we consider the communication complexity for the submodular maximization problems, and we show its application in streaming and robust setting. This is a joint work with Morgan Feldman, Ulva Svensson, and Rikosen-Clausen. So let me define the problem. So in this problem, we are given a set function that for any ground set W, it returns a positive value for any subset of this ground set. And we call this function monotone if adding a value to a set only increases the value of this set. For example, if you have a ground set X, we add an element E to it, and we call it monotone if adding this element only increases the marginal contribution. We call it submodular if it has a diminishing return property. So basically, if you have two sets X and Y, adding an element to X should give more benefit than adding an element to the union of X and Y. For example, you can think as a normal like factor or other functions that have the diminishing return. So this problem has been studied in various settings like Metroid, Matroid, the knapsack constraint, but the main one in here, I think, is the cardinality constraint. In the cardinality constraint, we want to maximize the value of f of s while keeping the size of the s less than a parameter k. So this is a generalization of the k coverage problem. In the k coverage problems, we have some sets from a ground set of elements. And we want to choose some of these sets that we cover as much as possible. For example, in this example, if we choose the green set and the purple set, we cover 11 elements, which is the optimum for this case. So this problem has been studied in the offline setting, and we don't know that 1 minus 1 over E is tight. And it has various applications from machine learning point of view as well. For example, influence maximization and more or less any type of summarization, image summarization, talk summarization, video summarization, and so on. It's also an interesting problem from machine learning point of view. And it has also been studied in the distributed setting, and we again know that 1 minus 1 over E is tight in the distributed setting. So in this work, we focus on this. So in this work, we focus on the streaming setting. Prior to this work, we knew that there are algorithms that achieve 1/2 approximation, and there was an upper bound of 1 minus 1 over E. And in a recent parallel work, this upper bound has been improved to 0.58 approximation. So at this point, the gap is between 1/2 and 0.58. In this work, we show that basically 1/2 is the correct answer and it's tight. So let me just give 1 minute overview of our approach. First, we focus on the two-player communication. We have Alice and Bob, and Alice sends some message to Bob, and Bob should give the output. In this case, we show that if the goal is to maximize a submodular function, we show that basically 2/3 is the correct approximation ratio unless the memory is basically huge and Alice can send more or less all her elements to Bob. And then we show that the algorithm that we design and gives a two-third approximation can be applied to the robust submodular maximization setting and get a two-third approximation. In this setting, the best known was 1/2. We also extended this to the multiplayer communication, which is basically, one can think of it as a special case of streaming submodular maximization, and we show that 1/2 is tight, which is the main result of this work. I think here is a good place to finish the talk. Thank you. I would be happy to answer some questions. I cannot hear you, I guess.
Any chance, so it's on the Q&A for people to read. Any chance this approach works for maximum coverage when sets are arriving one by one?
Yes, so for that case, we knew that 1/2, the 1/2 approximations, and the hardness result that we have, it also works for the coverage function. Basically, it's for coverage function, which is the special case of submodular maximization.
Questions? Question? Okay, then let's thank Askan. And yeah, there's one more question. So yeah, could you please give a high-level overview of the techniques used in the tightness proof in the two-player setting?
Okay, let me just go to the slide. Okay, so for 2 players, so okay, so from the hardness point of view, if let's say Alice has some elements and she cannot send all of them, so she should choose some subset. For Alice, we basically give her a lot of random elements from the entire universe, and then she can just choose a few of them basically, and then we guarantee that the solution that Bob has is basically an extension to one of the solutions that Alice has. And because they are all random for Alice, Alice does not know which one is the correct solution. And then she cannot basically distinguish between them. And any sets of elements that she sent to Bob has a big intersection with the elements that Bob has. That's the general overview. So I can go to the slides if you want. So this is for the general players, but we want 2 things, the gap value and indistinguishability. Because it's random, it's indistinguishable. And the gap value that we get in this case is 2/3.
Let's thank Ashkan and all the speakers. Session more or less concludes stock session. I will unmute all participants. So we will stop the live streaming and recording, but people can hang around and chat with the speakers.